Hello everyone, welcome back. So in this video we are going to see about DSBSC modulation technique. Okay, so DSBSC modulation technique. Okay, so if you are first time to my channel, please consider subscribing. Sorry. So DSBSC stands for double sideband suppressed carrier. Okay, so suppressed carrier. So what is the ideology or what is the basis for the formation of this modulation scheme is, again, it is a derived concept. It is again derived from amplitude modulation only. That is why if you understand amplitude modulation perfectly, then you can easily understand DSBSC modulation. Very simple. So the main disadvantage which we have found in AM modulation scheme is, so the time domain equation I am writing here, AC cos 2 pi FCT plus AC Ka m of t into cos 2 pi FCT. So this is only carrier. Okay, so this is only carrier and this is sidebands. Okay, actually sidebands only contains the message signal m of t. So we have seen that 67% of the total power being transmitted, out of 100% of the total power being transmitted, 67% is utilizing for transmitting only carrier, which does not contain any information, and the remaining 33%, around 33%, is utilized in transmitting sidebands, which actually contains information. That means the power is going to be wasted. How much? 67% of the transmitted power is being wasted. So if we can suppress carrier alone transmission in AM, if we can suppress the carrier alone transmission in AM, what will happen? 67% of the total power being transmitted, 67% of the total power being transmitted can be saved. Okay, so power can be saved. So this wastage of power can be eliminated when we suppress only this carrier alone transmission. So when we suppress carrier alone transmission, 67% of the total power being transmitted can be eliminated. Okay, so that is, this fact gave rise to new modulation scheme. Okay, so this fact gave rise to new modulation scheme, which is called as double sideband suppressed carrier modulation. Okay, so the term suppressed carrier does not mean we are suppressing the entire carrier. Okay, so entire carrier is going to be suppressed is the wrong word. Okay, carrier alone transmission is being suppressed. We are not suppressing the carrier, total carrier here. So if no carrier is there, then there is no transmission of the message signal from the transmitter to the receiver. Okay, again it violates the modulation concept. Okay, so it violates the modulation concept. Okay, so the concept here is carrier alone transmission. Okay, so carrier alone transmission is being suppressed, but not the entire carrier. Okay, so that is why still in sidebands there is the product of modulating signal, that is message signal, and the carrier signal. Okay, so suppressing carrier means we are not suppressing the entire carrier. Carrier alone transmission is being suppressed. Okay, so this is the basis for the formation of double sideband suppressed carrier modulation. So if the carrier alone transmission is suppressed, we can save 67% of the total power being wasted in the case of AM. So this fact gave rise to new modulation scheme, which is also again a derived scheme from AM, so which is called as double sideband suppressed carrier modulation. Okay, so we are going to suppress the carrier. So S of t of AM is given by AC cos 2 pi FCT plus AC Ka M of t into cos 2 pi FCT. So from AM we are going to suppress this term, that is carrier alone transmission is being suppressed. So we are getting the DSBSC. So what will be the time domain equation of DSBSC? So in DSBSC modulation scheme, Ka is going to be 1. So mu is greater than 1, that is over modulation case, and percentage efficiency is 100%. Percentage efficiency is 100%. Why? So we are transmitting now only sidebands only. We are transmitting only sidebands. So the total power is utilized in transmitting sidebands only. So PT, the total power which we are transmitting, is utilized in transmitting only sidebands. So PT is equal to PSB. What we have for efficiency formula, PSB by PT into 100%. So since PSB is equal to PT, so this becomes 1 into 100%. So this is equal to 100%. So efficiency is 100% in the case of DSBSC. Okay, so very important point, you just have to remember. And Ka is going to be 1 and mu is going to be greater than 1. So all these values you have to remember. So when K is equal to 1, then what will be the time domain equation of DSBSC signal? So K is equal to 1, so it will be M of t into AC cos 2 pi FCT, that is M of t into C of t. Okay, so this is the time domain equation of DSBSC signal. Okay, so it is again derived from AM signal only. Okay, so that is why I'm telling you. So if you learn AM perfectly, you can easily learn DSBSC. Okay, so this is the time domain equation. So what will be its corresponding frequency domain equation? S of f, that is applying Fourier transform on both sides. S of f is given by, so AC into AC by 2 into M of f minus FC plus M of f plus FC. Okay, so this is from modulation property. Modulation property of Fourier transform. So modulation property of Fourier transform states that AC into M of t into cos 2 pi FCT. So if M of t Fourier transform is M of f, if it is multiplied by AC cos 2 pi FCT, so its value is AC by 2 into M of f minus FC plus M of f plus FC. Okay, so this is the frequency domain equation of DSBSC. So if M of f is given by like this, it is a band of frequencies. Okay, normal case as we have seen in AM also. So if M of f is like this, W2 minus W. Okay, so if this is your M of f, then how will be S of f? So S of f, if you draw this, that is the frequency domain representation on this spectrum. If you draw, so what will happen? So M of f is now shifted to FC. So M of f is shifted to FC. Just we have seen in the case of AM also the same. So if it is shifted to FC, so this will be M of f, of course. So FC, this is FC plus W and this is FC minus W. And now in the second case it is shifted to minus FC. Okay, this is minus FC term. Okay, so this will be minus FC plus W minus FC minus W. Okay, so these arrow marks are just shown for your reference only, but actually there will be no signal present at FC. There will be no signal present at FC. So here also there will be no signal present at FC. Only you will have these terms. Okay, only sidebands. So this is upper sideband and this is upper sideband, and this is lower sideband. This is lower sideband and this is upper sideband. All the frequencies greater than FC are having lower sideband only. So this is upper sideband. Okay, so still if you find bandwidth is highest frequency minus lowest frequency in positive frequencies. So FC plus W minus FC minus W, which becomes 2W, which becomes again 2W. So there are two sidebands present, only sidebands, no carrier term. So this is only for your reference I have drawn, but actually there will be only sidebands present. Okay, so upper sideband and lower sideband, so both sidebands are present. So still bandwidth is equal to twice the message signal bandwidth. So here message signal bandwidth is W hertz and message signal bandwidth of DSBSC signal is 2W, that is twice the message signal bandwidth. So bandwidth of DSBSC signal is also twice the message signal bandwidth, which is same as in the case of AM. Okay, so from AM to DSBSC bandwidth is of no change. Okay, still the bandwidth is same, that is twice the message signal bandwidth. Okay, so this is about the frequency domain representation of DSBSC signal. Okay, so we have seen so I have drawn the spectrum. Okay, so I have drawn the spectrum, so I'll just show it again for you very clearly. So this will be minus FC, this will be minus FC plus W, this will be minus FC minus W. Okay, so this will be minus FC plus W. So this will be FC plus W, this will be minus FC minus W. Okay, so there will be no AC here. Okay, so this is upper sideband and this is lower sideband. This is LSB term and this is again LSB term and this is USB term. Okay, so still bandwidth, if you want to calculate, FC plus W minus FC minus W, so it is again equal to 2W only, twice the message signal bandwidth. Okay, so now we'll see the case of single tone modulation, single tone DSBSC modulation. Okay, single tone DSBSC modulation. So in single tone DSB modulation, so M of T is represented by AM cos 2 pi FM into T. Okay, the message signal consists of single frequency, then the process of modulation is called as single tone modulation. Okay, so S of T of DSBSC is AC cos 2 pi FCT into M of T. Okay, so now M of T is substituted with AM cos 2 pi FMT, so AC cos 2 pi FCT into AM cos 2 pi FM into T. So AC AM by 2 into 2 cos 2 pi FCT into cos 2 pi FM into T. So this is of the form 2 cos, just I have multiplied and divided by 2. Okay, so finally the single tone DSBSC signal is given by AC AM by 2 into cos of 2 pi into FC plus FM into T plus cos 2 pi FC minus FM into T. Okay, so this is the standard single tone DSBSC time domain equation. So this is representing USB. All the frequencies greater than FC represents USB and all the frequencies less than FC represents LSB term. So both the sideband are present, so it is called as double sideband suppressed carrier. Okay, so this is the standard time domain equation. So if you want to write the frequency domain equation, that is applying Fourier transform for this equation, if you apply Fourier transform, so what will be this? AC AM by 4. Okay, AC AM by 4. We know that the Fourier transform of AC cos of 2 pi fct is AC by 2 del of f minus fc plus del of f plus fc. So there will be two impulses. Okay, one is plus fc and other is at minus fc. Now in the place of fc we have fc plus fm. So using this concept applying to this signal, the first signal, we'll get two impulses. So amplitude also gets divided by 2. So ACAM by 2 divided by 2 is ACAM by 4. Okay, so into del of f minus, so fc in the place of fc we have fc plus fm. So f minus, so del of f minus fc plus fm plus ACAM by 4 into del of f, so one minus is completed, so now f plus fc plus fm. Okay, so this is due to the first term, that is upper sideband. Now lower sideband, in the case of fc, now we have fc minus fm. So plus, again the amplitude is same, ACAM by 2, so it's get divided by 2, so you'll get ACAM by 4 only into del of f minus, so del of f minus fc minus fm, f minus fc minus fm. Okay, plus last term ACAM by 4 into del of f plus fc minus fm. Okay, so this impulse is at frequency fc plus fm, this impulse is at frequency minus fc minus fm. Just equate the term in the brackets equal to 0. So f plus fc plus fm is equal to 0. So f is equal to minus fc minus fm. So this frequency is minus fc minus fm. The impulse is at minus fc minus fm. This impulse is at fc minus fm, and the last impulse is at minus fc plus fm. Okay, so I am drawing the spectrum based on this. I am drawing the spectrum. So this is S of f and this is f here. Okay, so there is one impulse function at fc plus fm. So if you assume this as fc, there is an impulse function at fc plus fm beyond fc, so fc plus fm, and there is impulse at minus fc minus fm. So if you take this as minus fc, there is an impulse function at minus fc minus fm. Okay, and third impulse is at fc minus fm, so fc below fc. Okay, so this is fc minus fm impulse function, and there is an impulse function at minus fc plus fm, so this will be minus fc plus fm. Okay, so all the impulses are having same amplitude, which is equal to ACAM by 4, ACAM by 4. Okay, so this is the spectrum of single tone modulation. Even if you find bandwidth in this case also, bandwidth is equal to, so highest frequency is fc plus fm, so this one fc plus fm, fc plus fm minus the lower frequency is this one fc minus fm minus fc minus fm, so you'll get again 2fm, so twice the message signal frequency. Okay, so in both, in the case of normal case, that is normal bandwidth is also equal to twice the message signal bandwidth, and in single tone case also it is equal to twice the message signal bandwidth in the case of DSBSC. Okay, so we have seen the time domain equation for single tone DSBSC is ACAM by 2 into cos of 2 pi into fc plus fm into t plus cos 2 pi into fc minus fm into t. Okay, so from this, if you want to calculate the total power also, so I have told you power is obtained from AC cos 2 pi fct is the AC term, so power is obtained from first finding its RMS value. So this is the maximum value, so from the maximum value we have to find the RMS value and we have to take the square of it to obtain the power. Okay, so P is equal to obtain like this. So this is one cost term and this is another cost term, so the amplitudes are same, so ACAM by 2. So first I am finding the RMS value, so 2 into root 2. and taking the square, you'll get the power in USB. Okay, so power in USB, so this represents power in USB term, plus AC AM by same, amplitude is same, so 2 root 2 whole square, so this represents power in LSB. So total power is equal to power of USB plus power of LSB. So this becomes AC square AM square by 4. Okay, so total power in the case of DSBSC, okay, so total power in the case of DSBSC is given by AC square AM square by 4. And since Ka is equal to 1, so mu is equal to Ka into AM, so Ka is equal to 1, so we can write mu is equal, almost equal to AM, so we can write AC square mu square by 4 also, in order to have the power, total power comparison between DSBSC and different other concepts. Okay, so this we'll discuss later. So AC square mu square by 4 and AC square AM square by 4. So this is the total power in the case of DSBSC signal. Okay, so and we know that the modulation efficiency is 100%. Okay, so these are the important concepts. Single tone modulation we have seen, bandwidth we have found for that, and general case for a band of frequencies, what is the bandwidth we have found, and we have drawn the spectrum also, and we have find the total power and modulation efficiency in the case of DSBSC. So these are all the concepts present in DSBSC. So in the next video we will go for generation of DSBSC signals. Okay.